Good morning. This is the example number 1 of section 16.4. So we have here a link AB that is rotating, like we can say that is, let us draw our coordinate system x, y, and it's rotating, right? They say that for an angle of, for 60, theta equals 60 degrees, we have a velocity of 5 meters per second of this linear velocity of this link, right? And we have an acceleration of 2 meters per second squared. And they want us to find, for that position of 60 degrees, angular velocity and angular acceleration. In this case, we will use absolute approach, so we have to find a way to relate those velocities that we are given with this angle in a generic form. So what I'm going to do is relate this distance, I'm going to call it x. I'm going to relate this distance, which will give me a relation with this velocity and acceleration with theta. How do I relate this theta with this acceleration? So I have the length of that line AB, and I can notice that the length of AB times cosine of theta will be equals to x. So let's write here the solution. So I will relate x with theta, and to do so I will say that x is equals 0.2 meters. I'm going to work in meters per second, not in millimeters, right? Times cosine of 60 degrees. When I do 60 degrees, this is the position for that instant. But if I want to find the angular velocity, I cannot use the position for that instant. I have to use a generic position to be able to derivate. So in general, x is equal 0.2 cosine of theta. So that's the expression that I will be able to derive to find the velocity. And that velocity, as you see, is a linear velocity that can relate to that velocity that I'm given for that position. To find velocity, I know that the velocity is the derivative of x with respect to time. That will be the velocity in x, which is the one that I can relate in this with this velocity. So the derivative of that will be x, the derivative of x over time, I can write it as x dot, and will be 0.2, which is a constant, times the derivative of cosine, which we know is sine of theta. But since I'm deriving respect to time, it's very important that you do not forget the internal derivative of that sine, which is theta dot. And that theta dot is actually our angular velocity. So from here, we could say that for theta equals 60 degrees, we solve for theta dot, and we have x dot 0.2 over sine negative, right? Negative. Don't forget the sine theta. And for 60 degrees, that will be that velocity that is given, so I will call that x dot, and since it's going against my to the left and x is going to the right, I can say that this is negative 5 over negative 0.2 sine of 60. So from here, theta dot, so which is my omega, which is theta dot, and I plug the numbers here and I can give you the solution, is 28.9 radians per second. So what about the angular acceleration? So to find the angular acceleration, I will make the derivative. Acceleration is the derivative of the velocity respect to time, or the second derivative of the position respect to time. And this is in x. I have to derive this generic expression. I cannot derive the one that I already plug in the values, because this is a constant, I have to derive the general equation. So it's the derivative respect to time of this expression right here, 0.2 negative sine theta, theta dot. 0.2 is a constant, and I can actually also plug the negative sign outside, and I will have the derivative of the product. So that will be negative 0.2. So it will be the derivative of the first, which is cosine of theta, times theta dot, which is the internal derivative, times theta dot, which is the second. So what I did here is the derivative of sine, which is cosine, times the internal derivative, which is theta dot, times that theta dot. Now, I have sine theta times the derivative of theta dot, which is theta 2 dot. So, and that expression is the one that I will use to solve for theta dot, which is the angular acceleration, and I will use those values that I'm given to be able to solve it. So the expression here will be x2 dot, which is the acceleration in x, will be equals to negative 0.2 cosine of theta, theta dot square plus sine theta times theta 2 dots. Solve for theta 2 dots, and I get x2 dots plus 0.2 cosine of theta, theta dot square, right, over, this is 0.2 times negative 0.2 sine of theta. For theta equals 60 degrees, I have that x2 dot is equals to negative 2 meters per second square, right? And I already have theta dot, which is this value, so I substitute and I get that alpha, which is theta 2 dots, will be equals to negative 470 radians per second square. Okay? So we finally got that the angular velocity is 28 times 9 radians over second, and the alpha, which is theta 2 dots, is negative 470 radians over second square. And we were able to relate the motion, the angular motion of this link to the linear motion of that other link. You can have also take a look of the PowerPoint solution, and it's right here.